Does this ever happen to you?
Just going to set my cruise control here.
Alright, let's see what's going on here. Yep, it looks like it's your transfer function.
So our problem that we're tackling right now is we're designing a cruise control system for an autonomous car. This cruise control will be able to speed up to a desired point and then hopefully maintain that point, not go too far over or under as well. And so for the model of our car, we have a mass to represent the mass of the car, a force, F for the engine, that's going to be the applied force that the engine puts on the car, and then a damper represents the friction to the wheels and the air resistance and drag from the surroundings. So here's our block diagram. As you can see, there's the damper, the mass, and then the force of the engine. And our specifications for this controller that we'd like to make is we'd like to have a rise time that's accurate for the acceleration of a car. We would like the overshoot not to go too far above the desired speed so as to stay under the speed limit. And lastly, we would like the steady state error to be minimal so that when the car finally accelerates to its speed, that it stays around the desired speed of the user.
So when we were modeling our system, the first thing we had to do was create a block diagram of our autonomous vehicle. And basically, so you have a damping coefficient, which is represented by B, and that represents air resistance and the drag force from air resistance. And you also have the mass is what moves, and that's just the mass of the car, and the force of the engine. So we solved the transfer function for this in terms of the force of the engine to the position of the vehicle. And we got 1 over ms squared plus bs. And we derived this to get the transfer function for velocity over force. And that's shown right here, 1 over ms plus b. And then we inserted some values for our damping coefficient as well as our mass. So for our damping coefficient, we estimated about 50 newtons times second per meter just for air resistance. And then the mass of the vehicle, we just used 1,000 kilograms. And then I can go over to the MATLAB code we use really quick. So we just plotted this transfer function. We use a unit step of 1,500 times g. That would be the unit step of the force of the engine and the impact this has on the transfer function. And we just use 1,500 newtons for this. And this is the plot we got. Levels out at 30 meters per second, and we'll go more into this later.
So based off this MATLAB plot, we find that the car settles at around 30 meters per second, around 65 miles per hour, which is a desired highway speed. Going into further analysis of this system, we bring it into the standard form, which is 1 over 50 times 0.05 over s plus 0.05. From that equation, we see that we have a pole in the left-hand plane at 0.05, meaning that it is indeed a stable system. Further analyzing it, we see that we have a gain value k of 1 over 50. Also, we have a sigma value of 0.05. From that, we can find the rise time and settling time. For the rise time, we use the equation 2.2 over sigma. With that, we come to a rise time of 44 seconds, which is very high for a car. That basically means that it'll get to 90% of our desired value in 44 seconds, meaning that the acceleration is quite slow. We also get a settling time of 92 seconds, meaning that it comes to about 1%, within 1% of that desired steady state value in 92 seconds. meaning that we're going to need a controller to bring these times down to a desired time.
Okay, so for a PI controller, our transfer function for a PI controller is going to be Kp plus Ki over S. And the place that we apply that function to is going to be in front of the g of s equation in the block diagram. And so by multiplying the two together, we can get an equation that's going to resemble something like that, with Kps plus K on top and then that denominator at the bottom. And so with this equation over here for the closed loop transfer function, we can put it in a standard form. And by putting it in that standard form, we can apply our design specifications from the previous slide and use that to calculate the values for Kp and Ki. And by doing the hand calculations, we were able to get the Kp value to be 101.8 and the Ki value to be 12.1. Yeah. And another way that we can verify these controller values is by doing MATLAB by using the Zyzo tool function. And so if we look over here, this is, so we want to first Zyzo tool, we want to add in the first order transfer function, which is in this case 1 over 1000 s plus 50. And after doing that, we can add pole and zero locations in this root locus editor up here. And where I do mine. And so by right clicking, we can add poles or zeros. And in this case, for a PI controller, we want to add an integrator. Right? You don't have to press that. Yeah. And so after doing that, we can see that we can come to these graphs over here and pick out phase margin and frequency values that will be consistent with our design requirements. And after fine-tuning these Bode plots over here, we'll get a transfer function for the step response over here that will look similar to what the response, that will show the response to our input.
So here is our closed loop block diagram as we designed it in Simulink. We're having a reference velocity in the step of 30 meters per second. And then there is our values for the PI controller there and our open loop transfer function. And so as you can see by the Simulink simulation of it, our car does settle to the desired value of 30 meters per second. There is some overshoot time, but the rise time is much better than the initial values. And so with the Nyquist plot for this, we can also determine that our closed loop transfer function is bibostable. As you can see, there is no encirclements clockwise of -1, and all of the poles on our open loop transfer function are real values. So that means that it is a stable transfer function. And so if we look back on our design specifications, we met that our rise time is less than 20 seconds. We actually got it down to 14 seconds. Our overshoot ended up being pretty close to 10% over the desired speed of 30 meters per second. We ended up reaching 33.4 meters per second. And then our steady state error is 0. As the time goes to infinity, the car will go to exactly 30 meters per second. So all of our design specifications were met with our controller.
All right, so the robustness of our system is also really important. How much your gain can change and how much time delay you can have in your system with the system remaining stable. So we calculated that over here. We have the Bode plots put up here, and we calculated the phase margin by finding the crossover frequency of the Bode diagram, which is when the magnitude crosses 0 decibels. And we follow that down onto the phase diagram, and we found that the phase margin of this system was 134.3 degrees. The crossover frequency, the phase is 47.3 or 45.7 degrees at this time, so 180 minus that is 134.3 degrees. And you can see on our phase diagram that the phase never crosses negative 180 degrees, which means that our gain margin would be infinite. All right, and so we also made sure our calculations were correct, verified it in a more realistic simulation in Simulink, and we put an input of 100 as a gain in our Simulink setup. And as you can see, your rise time is 0, which is a little unrealistic for our situation, but this proves it has 0 steady state error and our system is still stable. All right, so after everything's been said and done, we were able to take our system, the autonomous car, the cruise control on that system, model the entire system in a block diagram, get a transfer function from this block diagram, and then design a PI controller that can achieve our goals, which is a rise time under 20 seconds. We got 14 seconds and a reasonable overshoot, so you're not speeding too much, and 0 steady state error. So when you choose a speed for your car to go, you're at that speed, you've met that speed for the entire time, which are all the components of a good cruise control system. Thank you.